Welcome to the Applied Math Seminar. Today is going to be a seminar on fluid dynamics. Our speaker is Yohann Duguet from LISN in Paris. I'll let Yohann explain what LISN is. He did his PhD in 2004 at École Centrale de Lyon on rotating cylinders, if I remember well. Yohann, you tell me if I'm wrong. And undertook two postdocs, one with Rich Kurzweil in Bristol and one at KTH, both on fluid dynamics. And since then, he's been a CNRS researcher in Paris. And perhaps the best thing that I can say to introduce him is to say that he's one of the main actors in the development of our understanding on transition to turbulence and shear flow instabilities. And I think that would sum up pretty much Johann's contribution in fluid dynamics. Okay, Yohann, up to you.
Okay, so thank you, Cedric, for the invitation. So it's my pleasure to, be here. I'm in Paris, actually, at home today. It was planned that I would come physically to Leeds to give this seminar because I was traveling in the UK. Unfortunately, I had to come back, so I apologize for not giving the physical talk. But I'm around and happy to answer questions, so either during the talk or afterwards. So what I would like to tell you about today is a problem of transition to turbulence. And namely, I would like to tell you about simple turbulent shear flows in a channel. So it's essentially the simplest geometry you can think about. And in general, people who study turbulence have an obsession about trying to reach the highest Reynolds numbers ever, so to make the flow as turbulent as possible. And here in this talk, I will attempt the contrary, which means I will attempt to describe to you the simplest turbulent flow we can have in a channel by focusing on the lowest Reynolds numbers at which this flow can be observed. So it's a difference of perspective. So let me simply introduce colleagues, co-authors, location, etc. So I work now I'm employed by CNRS, which is the French equivalent of EPSRC, if you want. The lab to which I belong is part of University Paris-Saclay, and it's called LISN, which is a laboratory for interdisciplinary computer science. Everything dealing with numerics and computers. It's a big lab that got set up recently. So the collaborators that I have, they're not necessarily all from the same lab. So I will mainly focus on the PhD work of Pavan Kashyap, who has left LISN to go to Bangalore now. There's also contribution from Olivier Dauchot at the SPCI Paris and other colleagues, including Björn Hof and students at IST Austria near Vienna. Okay, so the main question I want to address first as an introduction is the question of transition to turbulence in shear flows. Shear flows means that I have fluid flowing next to a wall, and the interaction with the wall is crucial. So the way to introduce this problem is usually by turning on a faucet. So from left to right, I'm increasing the flow rate, as you can do every morning. So what you can see is first that the water, if it's water, flows in a very transparent way on the left. And as I increase the flow rate and turn off stronger and stronger, you can see that the flow of water becomes opaque to the eye, which means that in practice it's getting turbulent. It's flowing with a lot of vortices inside it. Now, if I suddenly decide to decrease the flow rate, what happens, and as a peculiarity of interaction with walls, is that the flow reverts from turbulent back to laminar, but not necessarily at the same flow rate at which it underwent transition from laminar to turbulent. So this is called hysteresis. And this has obviously energetic consequences if you want to run your pipe or run an airplane through an atmosphere. So we need to understand this hysteretic transition. So in principle, there's a recipe, there's a mathematical recipe to study the stability, the linear stability of any flow, including any dynamical systems, because this Navier-Stokes equation that govern the fluid motion can be seen only as a boring dynamical system. So the idea is to find first an equilibrium solution, so a steady solution of the equations of motion, which we call laminar. And then we ask the question, is it linearly stable or not? So we take the equations, the governing equations, we linearize around them, and we study the spectrum of possible perturbation. If all the perturbations are linearly stable, we deduce that the laminar flow is stable. And if one of the eigenvalues turn out to have a positive real part, then we deduce that there's an instability to infinitesimal perturbations that will saturate at a finite amplitude. And now we take the new state at a finite amplitude, and we linearize around this new state. And then until we find a new bifurcation, and so on. And after a finite number of bifurcations, these cascades into a turbulent flow. So that's the classical recipe. Does that work in practice, especially with flows next to walls? So here are classical academic flows from textbooks that are known to basic fluid dynamicists. So does that method of linearizing around a flow and deducing a cascade of bifurcations, does it work? In fluid convection, Rayleigh-Bénard convection, it does work, yes. In Taylor-Couette, which is the flow between two concentric cylinders, in general, it works and yields, positive results. In the flows that I care about, so flows in a pipe, flows between two moving walls, flow between two walls with an applied pressure gradient, flow in a wind tunnel in a boundary layer flows. Either it doesn't work or it works, but it's essentially misleading results. And this will not predict where transition occurs. So what I want to do today is focus on a given example and work it out more precisely using numerical simulation. So very little analytics, some experimental results, but not many. So I want to focus on geometry, which is the following one. Two plates, parallel, infinitely large in practice, and there's a pressure gradient applied from left to right, or it can be gravity or any body force that acts on the fluid and makes it move from left to right. So this is equivalent to the action of a pump, for instance. So we'll call X the streamwise direction, Y is the direction between the walls, the wall normal direction, and Z, the third direction, is the spanwise direction. And the gap between the plates is 2h. So if we consider this flow, this is actually a classic of linear stability theory. I think that the results go back to probably the work of Heisenberg earlier last century. It was considered as an alternative to cylindrical pipe flow, just to avoid cylindrical coordinates, I think. So there is a steady solution in this problem, so a flow that doesn't depend on time and has a parabolic profile in the direction y. So what about the stability of this flow? So first we need to define a governing parameter. It will be the Reynolds number. We'll define several Reynolds number, but the classical one is based on the centerline velocity of the laminar solution. Once you fix that Reynolds number, you fix the flow rate. So RE, and it was found and well tabulated that this laminar flow is linearly stable to all perturbations below a Reynolds number of 5,772. And the perturbations to the flow that break this stability at the critical Reynolds number are spanwise vortices. That's quite important. Spanwise vortices. So there's a textbook scenario that tells you that above this Reynolds number, spanwise vortices will amplify saturate, and then undergo a cascade of instabilities. And this is somehow true. Yet I'm interested in knowing how low you can reduce the Reynolds number and still keep turbulence. And I will show you this number is not relevant for this. So one of the first puzzles we see is to look at how the structures are oriented in this flow. So here this comes from, let's say, from sketches. On the left here, I'm showing you spanwise vortices. You see that they look like tubes orthogonal to the x direction, and this is the shape of the vortices in the associated with these critical modes, the so-called Tolmien-Schlichting waves. Now, the vortices that you would see in a turbulent flow, if I sketch them, they tend to be streamwise oriented, not spanwise. So this is brutally different. And this tells us that these Tolmien-Schlichting waves are not telling us much about the turbulent flow. So we will go into more details now. Experimentally, how low can we go down and in Reynolds number and still observe some transition to turbulence? So linear stability theory has failed. So it means that if we manage to, I will explain how, if we get turbulence at a lower Reynolds number, it's in the presence of a linearly stable laminar flow. So it means that this turbulence is due naturally to finite amplitude transitions, perturbations only. So at Reynolds of 1000 with the same definition or a bit higher, people have noted in experiment that if they simply bang on their channel with the water flowing, they can, and if they bang hard enough, they can have a turbulent, a spot of turbulence, and that spot would grow and tend to invade the flow as it is advected downstream. So we will call that turbulent spots. This is related to the proliferation of the turbulent flow. So you see, this turbulence is disconnected from the laminar flow. It doesn't emerge through a linear instability. So now we want to reduce the turbulent flow, the Reynolds number of the turbulent flow. So what we should do is simply forget about linearizing about the laminar flow, which is the textbook method, and simply look at the turbulent state for what it is. And then look at the stability of the turbulent flow itself with respect to arbitrary perturbations, rather than focusing on laminar, because the laminar state is not a useful reference point. Okay, so this idea dates back from, it's 20 years old, more or less, or at least in the context of fluid dynamics. Try to look at the stability of the turbulent flow itself, or possibly its instability. So now I'm asking, in physical space, what is the simplest form of turbulence that these flows can take? At which values of the Reynolds number can they be found? And is it common to all shear flows, or should I focus on channel flow or pipe flow? So, okay, in pipe flow, it has been answered. If you reduce the Reynolds number, the simplest form of turbulence you can have is localized turbulence. So here, this is the side view of a pipe flow, so a cylindrical pipe flow. And you see patches of turbulence. Above it's in experiments, so it's using dye and a laser sheet. And the picture below, this is from direct numerical simulation. So we directly simulate in an unsteady way the Navier-Stokes equations in 3D. And this is supposed to represent the same structure with clear shape, arrowhead shape, let's say. It's called a turbulent puff. Okay, this is localized. This is turbulent pipe. And now I want to move to these planar flows. So what has been shown experimentally, it has not been necessarily well understood. interloquate flow between these two cylinders is still water flowing there, sheared between the two cylinders. It has been found that the flow organizes at the lowest Reynolds number in some kind of laminar turbulent alternation with an interface between laminar and turbulence that is oblique with respect to the mean flow. In other flows, Planck-Wade flows, so this is the planar equivalent where the fluid is shear between two parallel plates, it was also found that there's a structuration of the flow in dark laminar band and whiter turbulent areas. Also with interfaces oblique with respect to the mean flow, with an angle close to 30, 40 degrees. We can discuss this. Here, this is a rotor-stator flow. Again, black patches representing laminar flow with some non-zero orientation with the laminar flow, with respect to the mean flow, sorry. This is annuloquate flow, is another geometric variant of this. Again, an interface with some obliqueness. So that seems to be a common property. And we decided to look for it in turbulent channel flow. So here I only wrote the equation just for the non-specialist to remember that the Navier-Stokes equation in incompressible fluids have this form. So UL and well, capital P that you don't see is supposed to be the laminar flow. And these are the linearized, sorry, not linearized, the nonlinear equations written as perturbation of this laminar flow. The flow is incompressible. And more important than the equations themselves, probably the boundary conditions will simply imply two things. No slip at the wall, so Dirichlet condition U equals 0 at the walls, to tell you that the fluid cannot, you know, just sleep at the wall. And because it's convenient in numerics and the flow is open, we impose periodicity in the streamwise and spanwise direction. And we can discuss afterwards the consequences of this. Okay. So now let me introduce the length scales in competition, else you will have a hard time understanding the Reynolds number. So there's a global, like large scale that is the half gap between the plates, H, 2H is the gap. That's the usual one. We can construct our Reynolds number on this. There's another one that is local, and he ignores completely the geometry of the channel. It's the one that is induced by the imposition of the wall, the shear rate at the wall. So this one, when you impose a fixed pressure gradient or fixed gravity, this is a constant. It's imposed by the pressure gradient. It's a shear rate. Dimensionally, you can define a friction velocity u tau based on this. You know? And from this velocity u tau and the knowledge of the kinematic viscosity of the fluid, you can reconstruct another length scale, delta nu, which is different from h, and it's only local. It's really the length scale due to the fact that the slope of the velocity profile is known at the wall. So now we have to play with two length scales. One is h, the other is delta nu. Clearly, you can define the ratio between the two, and this is what people in wall turbulence do every day. H by delta nu, this is equivalent to a Reynolds number, which is called Reynolds tau. So it's the friction Reynolds number. So it means the larger scales of the flow divided by the smaller scale, like a Kolmogorov scale. So it really plays the role of a Reynolds number. The larger it is, the more multi-scale it will be. And there is also the classical Reynolds number based on the properties of the laminar flow, RECL, CL like center line. And they are related if you impose the pressure gradient. So Reynolds tau and RECL are related by this, this relation here at the bottom. Okay. It turns out that I will impose the pressure gradient, therefore I will play with the parameter Reynolds tau rather than an RECL. That's the complication, not a huge one. So it was actually simulated in the years 2000 that if you consider turbulent channel flow and make the domain large enough and reduce the Reynolds number, yes, these laminar turbulent interfaces oblique to the mean flow have been found. This is numerics by Tsukara in Japan. So they've been observed but not necessarily understood. And well, my goal later was to, take available DNS codes and simply verify all this myself. So that was where Tsukara stopped. He identified, here's the classical Reynolds number, and he identified flow states. So above, close to 2000, he saw what he called featureless turbulence, perhaps stripe patterns below, and at even lower Reynolds number, turbulence seems even more sparse. So in very recent experiments, it's from 2019 in Austria, in a long channel by inducing perturbations by hand at the entrance of the channel, they could also observe these structures. But it's not clear how much they converge in time. So do we reach the attracting regime of turbulent Poiseuille flow? This is not clear with the length that they have. So at least they could find a Reynolds number experimentally close to 650, 660, above which the turbulent stripes tend to grow in length and below which they tend to retract in length. So simply by waiting when checking where the growth rate crosses zero, they could predict a transition from shrinking to expanding turbulent stripes. So that's the onset of proliferation, close to Reynolds 650. So this is probably the lowest Reynolds number below which you don't observe turbulence in experiments. This I will skip. So, okay, numerically, I will play with two types of domains. Since this turbulent laminar pattern seems to have some relevance to the onset of turbulence in channel, we will first consider numerical domain that kind of captures these turbulent patterns. And since they're naturally, we find out, have an orientation, a non-zero angle with respect to the x direction, we will assume that the numerical domain captures that orientation. It's the equivalent of what you do in linear stability analysis analytically when you impose the ansatz. Here, it's an ansatz in the numerics, but it's not linearized. If this is done, these are space-time diagrams. So here you see Z and versus time. So this is from the work of Tuckerman and Barclay. First, you get turbulence everywhere. And as the Reynolds number is reduced, you see that these turbulence bands start to appear. We will discuss later how. And at some point, they turn into solitary bands that just travel alone. Okay, so this I will skip. So we wanted to know from our own numerics using the code channel flow, can we go below this Reynolds number? And actually, yes, we managed. The turbulent flow wants to die below 660, but assuming this periodicity, we just went down slowly in Reynolds number, so pseudo-adiabatically. And below 500, here we're displaying the streamwise velocity, you can see that the flow gets calmer and calmer until it gets, well, almost periodic in time. Actually, there are two frequencies shown here. And that's it. And so here, the flow has just converged onto, so at this Reynolds number, it's a periodic orbit in a moving frame. So if I take, for instance, the upper diagram, this is a Reynolds number on the x-axis and energy on the right. on the vertical axis. And the chaos becomes transient below 616, as we knew. But by going down adiabatically slowly in Reynolds number, we managed to land on, well, essentially a simple unstable limit cycle, which we found, if you look at the inset, there's a stable limit cycle that actually bifurcates from it's the restabilization of an unstable one that has the property of bifurcating off a branch of traveling waves. All the states are spatially localized, or they form a pattern if you prefer. So that's it. We are very surprised by these results because just turning down the Reynolds number allows you to find a periodic flow. So there's a simple precursor of this turbulent regime that was not expected until now. And so we could then use the classical tools like Newton solvers and continuation solvers that go with this code channel flow, and simply reconstruct the bifurcations of these traveling waves. So they are disconnected from the laminar flow. They do not emerge as an instability of the laminar flow. Yet they appear at finite Reynolds number, or less than 400, all in saddle node bifurcation, and they draw different families according to the angle that we have imposed to the domain. So here are these solutions. So you see that they are localized and almost two-dimensional. They're not exactly like this. So these are new solutions. They're exact solutions of the Navier-Stokes equations. We are trying to understand whether we recognize a self-sustaining mechanism that explains why these solutions can exist as finite amplitude solutions at finite distance from the laminar state. So for us, they are the precursors of this pattern turbulence. Okay, now we'll move on to larger domains and a more experimental-like analysis of the onset of the turbulent flow. These are brand new results; they're not published yet. So here I only explained the parameters. What you have to remember is that these are heavy simulations, where we needed something like 4,000 processors for every simulation. The simulations are simulation in space and time, of course. So maybe we should watch this flow. So now we're interested in the onset of the turbulence starting from above. So how do you go from turbulence to a pattern turbulence? So what I will display here for every Reynolds flow, these are movies of the whole normal velocity fluctuation seen in the plane of the flow. So x, z. The direction that you don't see is the short direction normal to the world. So in the first movie here, you see the turbulent flow at Reynolds 100. Not much to see. Do not watch for too long. Epileptic people should not watch it. It's important. And now this is below at Reynolds 90. And so we're in a moving frame, moving with the flow. And if your eye is a bit trained, you can see that there are some large-scale modulation of size around 20, 30 half gaps in wavelengths. It gets clearer as you go down in Reynolds number. At 75, you see that these modulations are now finite amplitude modulations. And in a given zone, you see turbulence, and the green zones, you could almost say that the fluctuations are absent. So you would call it laminar turbulent patterning. And this is what you see at Reynolds 55. So turbulence gets sparser and sparser. If we continue to go down in Reynolds number, that's 45, things become to change because turbulence is so sparse that it becomes now like a gas. And the turbulent structures start to move relative to each other. and to undergo collisions. This is a much more difficult regime to describe, whereas above 450, Reynolds 50, clearly you almost had a steady pattern, broken, not so regular in space, but with a very simple dynamics in time. And this is 39 is the lowest we could achieve before it gets transient. So now we have a competition between different orientations. So this has been studied recently by Manville. We focused more on here on the upper regime. Indeed, if I come back to this first slide here, I want to understand the difference between the regime above and the regime below and try to explain why this modulation starts to pop up. The novelty here is that the regimes of laminar turbulent patterns is, as a predecessor, that is a modulated regime, and that simplifies our analysis a lot. So, so here I just want to show you one of these bands in isolation. There's something that is useful to understand is that it's not only turbulent in the middle of a laminar flow, it also, there's something at the interface, actually, and this explains somehow why it has this oblique shape. There is actually a large-scale flow close to the interface because there's an interface, and this can actually be understood in very simple terms analytically. It's actually a kinematic effect. So suppose that I take any velocity component and I define the overbar, which is simply the integral of that quantity or the average, or from one wall to the next. So I will two-dimensionalize the flow simply by integrating from wall to wall. So on first equation, I simply take the continuity equation that says that the volume of my fluid cannot change locally. I can apply large-scale filtering or not. It's linear operator, it commutes, so it's not important. And now I integrate in y. Interestingly, because y is the direction from wall to wall, the term in dv dy, the second one here, will vanish by integration. Even if whether there is slip or no slip, it doesn't matter. It's the impermeability at the wall that governs this. After integrating, you end up with a two-dimensional equation for a virtual two-dimensional fluid flow with vector field u bar, w bar only. And this equation tells us that this virtual two-dimensional fluid flow is incompressible in the plane xz. So that's a very strong property. Now, what it's telling you, if you suppose that you take this picture and you start from laminar or far on the left and you move and you cross the turbulent band. As you approach the turbulent band, locally the U bar, which is the streamwise flow rate, changes with respect to x. Therefore, du bar dx has to be non-zero. And this change of U bar can only be compensated, so the equation says, by a Z gradient of W bar. So it does so. And we end up with U bar non-zero and W bar non-zero. Therefore, there is a flow with U bar and W bar non-zero, which means there is a large-scale flow with a given non-zero angle. So this is simply derived from the kinematic equation. So this is why it occurs so fast when you watch the simulations. You know, it's not including momentum or inertia at all. Okay, well, here are some statistics of the flow that we could compile because we could. So this is the angle as a function of the Reynolds number on the left. The domains are huge, but they're still limited for what we want to achieve. And this is averaged in time. You can see that the angle rises from 20-something degrees up to 45, close to extinction. The wavelengths also similarly grow. So both the angle and the wavelengths grow. So we don't fully understand exactly why. I mean, the previous argument is just hand wave. It doesn't give you the angle, doesn't predict. More important is the onset. This is what I want to discuss now. So we can define a modulation amplitude simply by considering the spectrum in X and Z. There are many ways to do that, but here we plot this amplitude of the pattern versus Reynolds slope, and you see that it's never zero, but it takes off as you go down in Reynolds number. As you go below 90, then suddenly it starts to take off. So this is where we truly see by eye the laminar turbulent coexistence. Note one thing: we need to define things quantitatively, because else the movies will depend on which quantity I display, which ISO contours, etc. So just like in experiments, you can do very little out of visualization. So that's why we go quantitative and start to define these numbers. What we would like to do is find a way to define the onset of this turbulent laminar patterning without something that is threshold independent and quantity independent. So that's one of the most important slides of this talk. Here is the pre-multiplied spectrum. This is where the energy lies in average in the Kx, Kz plan. So you can see top right a huge blob, which corresponds to the small scales. And then you can see a smaller one in the small, so bottom left, you can see the small square. And you see that there's also energy there. And this is the energy of that modulation. Okay, so there's a nice spectral gap between the two. So what we would like to do now is to see whether we can reconstruct a dispersion relation for the so-called instability of the turbulent flow. But we don't assume anything about the turbulent flow. We don't take its time average or its spatial average, or we don't use any closure. We just take it as it is, and with all its complication in time and space, and well, see whether we can, perturb that turbulent flow, and see whether the systems can relax to it and measure something during the relaxation. That's the main idea. So what we do here is you can see this amplitude versus time in this plot. So for all the negative times, the system evolves. And at time 0, we decide to give an impulse, which means we give it a kick at time 0, finite amplitude kick, where we excite all wave numbers at once. And then we actually filter the results per wave number and look for each Kx, Kz at how the system relaxes in time towards the turbulent equilibrium. So if you do this, you get exactly what you see here in the black curves. So every realization returns to turbulent if you're high enough in Reynolds number, but not in an exponential way. However, we did it now 40 times per Reynolds number, which has a cost. And ensemble averaging the results and monitoring them versus time yields nicely this red curve, where we can see actually that there's an exponential decay back towards equilibrium. So by subtracting the saturation level and plotting that in log, then we can see comfortably a good old decay that we can fit. So we did that for every Reynolds number and every Kx, Kz. And then this is the growth rate we find versus K. So K is the total wave number, square root of Kx2 plus Kz2. And the different colors correspond to different values of Reynolds tau. So as you can see, using this ensemble averaging, we get a quite clean relation dispersion, a bit like you find in textbooks when you linearize around a homogeneous steady flow. But here we have linearized around something widely turbulent, okay? And we can see that somewhere between Reynolds to 94 and 96, the growth rate passes by 0 for a given k that corresponds to lambda x of 36h. And this is perfectly matching what we have measured from the DNS. This is the relation dispersion seen from another perspective, namely versus Reynolds tau for parameterized by k. And similarly, you see that the onset of this modulation is at 95, or between 94 and 96, which I call 95. And this is perfectly consistent with what could be seen. So interesting. Can we now discuss the origin of this instability? So there's an instability of the turbulent flow, at least in average. So the most promising idea we have at the moment is to look at the system using ideas that are rather exotic in fluid dynamics, but that come from biological studies. Namely, the Turing mechanism is our favorite one at the moment. So I will not give a lecture on the Turing mechanism, but what is it? It's an instability of homogeneous base flows, a linear instability in the presence of two agents that diffuse into each other with different diffusivity ratios, or diffusivity constants. It's found most of the time in the context of two-dimensional reaction diffusion systems of that form, where A and B are the two agents, dA and dB are their diffusion constants, and they're different. And F and G have a special structure. Namely, A is seen as an activator and B is seen as an inhibitor. This has something to do with the coefficients of F and A when they're written down. This mechanism has been invoked to, explain, more or less every pattern on Earth. It's not clear whether the description is actually relevant, but at least people have expressed this hypothesis that, namely, the way that those two agents diffuse into each other, if the inhibitor diffuses faster than the activator, then so it's summarized in the sketches that come from an equivalent of Murray's book, then an inhomogeneity can actually rise in versus time, and this is not included in mechanism, but can also saturate. So can we play this game with our laminar and turbulent flows? It's not obvious. First, we deal with PDEs, and there's an infinity of degrees of freedom, not only two. So can we, so as I said, it's not obvious at all, just to tell you that it also a very frequent explanation for vegetation patterns, not only zoology patterns. So two species, can we think of laminar and turbulent? So let's stay simple. If there's one of the two protagonists, which is the inhibitor, it has to be the laminar flow. Whereas the turbulent flow would be the activator. So if we play this, what are the diffusivities? Diffusivity of laminar flow is trivial, it's new, it's the viscosity of the fluid. The diffusivity of the turbulent flow, that's a much harder business. What we know, at least that dimensionally, it's a product of a velocity and a length scale. So if we assume that h is the length scale of interest and u tau, the friction velocity, is the velocity we want, expressing the Turing instability condition that the inhibitor must diffuse faster than the activator results in assuming that nu is larger than a constant times u tau h. But this, if you come back to the definition of Reynolds tau, this is equivalent to saying that Reynolds tau must be smaller than a constant. And this is the only, so this is actually consistent with what we see, that the instability of the turbulent flow manifests itself when the Reynolds tow is smaller than, well, here it turns out to be 95. We don't know many mechanisms to explain that an instability occurs as the viscosity is decreasing. This is not the usual way. Well, usually it's when it occurs when the viscosity, decreases, and here it's when it's increasing, so a decreasing Reynolds number. So therefore, we needed a specific mechanism. Okay, I'm nearly done. I just want to, just end this this talk with other rules of thumb that can be suggested, even simpler, to try to explain why the flow becomes turbulent in an intermittent way when you go down in Reynolds number. One is due to Alfredson Matsubara in 2000. It's not very well known also for turbulent people. It's just the idea that if you want to put streamwise vortices and you want them to survive between two walls, and their size is 100 delta nu, and they have to fit within 2h. Then 2h has to be larger than 100 delta nu, which means that the ratio h by delta nu, which is Reynolds tow, has to be larger than 50. And remember, our instabilities all come between 50 and 100. Even simpler rule of thumb that nobody had noticed is that this is the friction factor. So engineers, have played a lot with these diagrams. We see CF, so the friction factor, which is just the normalized wall shear rate on the vertical axis, and the Reynolds based on the bulk velocity on the x-axis. And laminar is in blue, fully turbulent is in red, and the zone where these laminar turbulent patterns are seen corresponds to CF equals, well, nearly a constant, 0.01. And we compare to all other flows like pipe flow, Planchet flow, etc. And when there are patterns, they always occur for CF equals 0.01. So is that maybe the simplest non-dimensional number that can describe our intermittency? Maybe, but we don't know why. Okay, so if we sum up, here is the bifurcation diagram that emerged in the last years for this flow. So the turbulent channel flow has been known for 100 years at least, but only now we start to explore the lowest range, the range where turbulence is in its simplest form, and it all occurs between 95 and 50. So it doesn't start with the intermittency regime doesn't start directly with laminar turbulent patterns. It's preceded by a modulation, and that modulation emerges in average as at 95, Reynolds tow 95, as an instability of the turbulent flow, taken all together with all the fluctuations, no closure, etc. Linearizing around closures of the turbulent flow has so far never worked. Else I would have started by this. And many other questions remain open. There seems to be a second transition below 49, the one that leaves the laminar turbulent pattern and turns towards a gas of turbulent stripes. This one we don't fully understand it. What happened below when it gets extinct? The current trend is to expect the scenario closer to directed percolation, so statistical physics. What we have shown today is that we can actually go below and find unstable solutions of localized form, like a skeleton underlying this directed percolation framework, maybe. An open question is, how universal is this? If I move to pipe flow, do I get the same phenomenon? Planchet flow, the same? We still don't know, actually. And what can we do with those simple rules of thumb that I discussed? Are they useful? Are they misleading? They seem to predict quite well the important critical values. They're never mentioned in textbooks, so should they? Okay, so I would like to conclude with this, and accept any question of any level. Don't worry.